Hey everyone, welcome back, and today let's solve Leetcode problem 73, titled Set Matrix Zeros. So very straightforwardly, we're given an m by n integer matrix, and if any element is 0, we need to set its entire row and column to zeros. And we have to do it in place, meaning we can't create another separate matrix to do these operations, we have to do it on the input matrix itself. So in example 1, we have our input matrix to be 1, 1, 1, 1, 0, 1, and 1, 1, 1 on the three rows respectively. And in this case, we see that there was a 0 in the second column in the second row. And so in the second column in the second row, we want to replace all the elements to be zeros. And so we get 1 on the outer corner cells, if you will, and zeros everywhere else. Very straightforwardly, if we apply that operation on the example 2 input matrix, we'd see that we hence set the first column, the first row, and the last column all to be zeros because there is at least one zero in all three of those areas, right? There's a zero in the first row, or rather there's two zeros in the first row actually. There's a zero in the first column, and there's also a zero in the last column, hence why we set all the other elements in those rows and columns to hence be zeros. So for the constraints here, we see that m and n are going to be the number of rows and columns in our input matrix, respectively. Both of those values are going to be between 1 and 200, rather small for, in terms of input constraints and runtime complexities here. And any value in the matrix itself is actually going to be between -2 to the 31st power and +2 to the 31st power minus 1. And they also give us a follow-up here. A straightforward solution using big O of m n space is probably a bad idea, and a simple improvement uses big O of m plus n space, but still not the best solution. They actually ask us to devise a constant space solution. I don't think entirely that is, super important, although I will be doing this in constant space, kind of answering that follow-up for this specific solution, just to kind of, tell you guys how to solve this in the most efficient way possible, right? So let's go ahead and get into how we actually can solve this problem in terms of main observations and kind of key takeaways to really make from these examples and problem statement here. And the first, big observation, if you will, that we really need to make to solve this problem most efficiently is that, especially in place, if you will, for that constant memory complexity, it's that every time we actually find a zero in the matrix, whether it be in its row or column, we know that the entire row and the column that containing it has to be converted to a zero. But since we are going to be solving this in place to answer that follow-up and have a more efficient memory complexity, if we actually start turning all those rows and columns elements to zero as we go, we might actually accidentally erase any data or make any other elements that we shouldn't touch yet to zeros that we haven't actually processed yet. Obviously, that wouldn't be right. That would interfere with our actual expected solution. And so you have to really think, okay, how can we actually remember which rows and columns have to actually be set to zero without any extra space, right? Because usually you'd need some data structures of some sort to be able to store those. Well, there's actually a clever trick behind this, and that is, instead of actually using that extra space here, we can actually use the first row and the first column of the matrix itself to actually store that information, to avoid even allocating that big O of m plus n space, storing everything and storing all that information all in the matrix itself in the first rows and columns. But even then, there still is a catch, because what if the first row of the column, what if it already contains a zero? That could still mess things up in how we actually store the information, and so we're hence going to be using two extra Boolean variables that don't obviously take up any extra space. The first would be, does the first row have a zero? The second would be, does the first column have a zero? Just to really literally keep track of, is the first row or column having a zero, if it's true or false, right? That's going to basically just help us remember if the first row or column originally in our input itself previously had any zeros before we actually made any operations. And let's go ahead and now see how that actually works in terms of code. So let me actually just get the editorial up here. And clearly it says that we don't have to return anything. We're just modifying the matrix in place for that constant memory complexity, right? So the first thing that we're going to do is actually just get the number of rows and columns quite straightforwardly and store them in integer variables like we usually do for matrix problems. So I'm going to call them rows. That's going to be the length of the input array matrix. That's really just a clever way of getting the number of rows. And the columns is going to be the length of the matrix at index 0. Just a simple way to get the number of rows in any given matrix, assuming its name is, of course, 0, right? And we're just storing those values in these integers, rows, and columns to help us really loop over the matrix later on and give us those corresponding lengths, right? Now, here we actually now have to initialize those two Boolean variables that I was talking about here. The first one was, does the first row have a zero? And quite literally, I'm just going to name those variables exactly that. First row has 0. All right, and the second thing is going to be first column has 0. And what is a kind of, simple, quick way, or rather I should say one-liner way to check if the first row has a 0? Well, for any cell in the entire first row of the matrix, if it's equal to 0, we have to set that equal to true, right? Because this is basically monitoring if we do have any zeros in the first row, and same idea, but for the first column. And a good way to do that in Python is using something called list comprehension here. We're going to be using the any keyword. If any cell in matrix at index 0 at index j, if it's equal to 0 for any j in the range of the number of columns we have, basically just going through the first row, if any cell value, that is, in the first row or column, or row 0, if you will, if it's equal to 0, meaning it has a value originally of 0, then we have to return or set that equal to true if any of that is true. Any of the cells, rather, in the first row are 0. And very, very straightforwardly, we have to check if there's a 0 in the first column to tell us if the first column needs to be zeroed out later. The way we can check that is if any matrix, in this case, at index I, index 0, if any of the values in that first column now is equal to 0 for every value I in the range of the number, in this case, rows we have, to go through the number of values in the first column, that is, to again tell us if the first column needs to be zeroed out, if we have any zeros in the first or second, rather first row or column. Right? And that's just really initializing those variables. Now we have to actually loop through the entire matrix to actually, treat the first row and column as markers and find if we find any zeros in them. Right? And the way we can do that is really just straightforwardly for I in the range. In this case, we have to actually start from the first row and first column because we already iterated over the first row and column to check if they had any zeros. They're going to be used as our storing information or markers, if you will. Right? And for j in the range of 1, in this case, columns, right? Just two straightforward nested loops here to go through every single cell value in everything but the first row and column in the input matrix here. If matrix at index I and index j, if we actually have encountered a 0 here, we know immediately, okay, we need to set this guy equal to 0. Why? Because, well, that's quite literally what the problem said, and we also need to set this guy's row or column also to be 0, right? Basically, if we find a 0 at any value I, comma j, we have to mark its row and column for zeroing, if you will, by first setting its row as 0, and then actually setting its, or marking its column, if you will, as 0. We're basically storing metadata, if you will, inside the matrix itself for corresponding rows and columns if we find any zeros in them. Right? That's a very key step that we do in place in the input matrix itself. Now that's just the first kind of markering or stamping part, if you will. Right? We have to actually have another cell to check if the marker in its row is true. Right? And the way we can check that is for I in the range from 1 to the number of rows. Again, another very straightforward loop here, or rather nested pair of loops, I should say. 1 to columns. Nothing different from the last iteration or the last pass, if you will. If matrix at the current value I, comma j, if that's equal to 0, or matrix at, it should be I, comma 0. Okay, interesting. Okay, wow. Slash just isn't working today. Matrix at 0, comma j. If that's equal to 0, we know immediately we have to set matrix at I, comma j to also be equal to 0. Now, why is this? Well, we're basically, again, doing that another pass here through all the cells, starting from row 1 and column 1 in the matrix, and for every cell, we're checking if the marker in its row, meaning matrix at I0 is 0, or if the marker in its column is 0. If either of those are true, we have to set that cell to 0. Why? Because we're using those markers that we set up in the previous pass to 0 to zero out the appropriate cells if we find any cells in rows or columns where their rows or columns are already marked off to be completely zeroed out, right? Which is what the problem statement confirmed us to tell, or rather confirmed to us. Now, here is where we actually use that those two if 0 and if first row has 0 and if first column has 0 to zero out any entire first rows or first columns that we hadn't done so yet. And the way we can do that is really if first row has 0, if first row has 0, meaning that's true, the first row did originally have a 0, we know we have to zero out the first entire row. And very straightforwardly, we can just do that by iterating over the number of columns we have, because that's going to give us the length of the number of elements in the first row, and set matrix at index 0, index j to be a 0. Basically just marking every element in the first row to be a 0 if the first row originally had a 0, which we can check in this Boolean array, or rather this Boolean statement, or this Boolean integer, sorry, or variable. And very straightforwardly, if originally the first row had a 0, sorry, there should be column. If originally the first column also had a 0, well then we know we have to also zero out the first column as well, meaning for I in the range of rows, that's going to give us the number of elements in the first column. And any column, if you will, we're going to set matrix at index I, index j, rather 0, to be a 0 as well, because we have to zero out the entire first column if the first column originally had a 0 or more, right? And effectively, that's it. We don't actually return anything like the problem statement tells us. Why? Because we're doing this completely in place, changing elements in place to the input array, and that's basically it. So unless I made the syntax 0, 0, this should be accepted, and there should be a valid solution. So let's go ahead and verify that. Okay, first, oops, there should be an S, not a Z. Sorry about that, guys. Hopefully this works now, unless I made another very simple error here. But as you can see, this really is just about as efficient as you can get it to be, right? So again, on a high level, how are we really solving this problem? Effectively, we're still doing this in place by kind of using that in-place matrix multiplication, or rather matrix manipulation, with that extra space optimization, right? Because really, at the end of the day, we're really just first scanning over the first row and column to see if they originally had any zeros. We're then looping through the matrix, and then whenever we actually find a 0, we mark its row and its corresponding column by updating the first cell of that row and column. That's the whole point of why we had that first pass for the first row and first column, and check if they had to be zeroed out as well. And then we actually used those markers to then zero out all the appropriate cells for any values that we found that were supposed to be zeroed out or marked rows or columns, and then we actually finally handled that first row and first column zeroed out case if they actually initially had a 0 or not. And all of this is done in place. We really don't have any extra space or any extra data structures except those two Boolean integers, those two Boolean variables, which don't take up extra space, right? So which brings us to the complexity of the solution. For the runtime complexity, very straightforwardly, we have a couple passes here, but all of them really are just on average big O of m times n. Even though we scan the matrix a couple times, they're always going to be big O of m times n time. Why? Because we visit each cell a constant number of times. M is the number of rows and n is the number of columns. And again, the memory or space complexity is still big O of 1. It is constant. We're not actually using any extra space or any auxiliary memory with any extra data structures that scales linearly with the matrix, or even worse. We're only using, again, those two Boolean variables and manipulating the matrix in place. And hence, this is going to be a big O of 1 or constant memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.